Good morning, all of you. Welcome to CJ Exam. So today we are discussing Electrochemistry lecture 2. In the first lecture, we have discussed about Faraday's laws and electrolysis, and more about electrolysis we'll discuss in electrode potential. And we have done some numericals based on Faraday's laws. Those numericals are enough for NEET as well as JEE mains. Now we are going to discuss more about conductivity, conductance, and resistance. So experimental determination of resistance of electrolyte solution. So to determine the resistance of electrolyte solution, meter bit circuit is used. At the balancing length, we have L by R, that is length by resistance is equal to 100 minus L by R of cell. These days we use digital conductivity meter, which gives conductance of the solution directly. So this is called meter bridge, or you can say Wheatstone bridge, which you will get in physics experiment. So here experiment is not required to discuss. Just the balancing length we can find out by using L by R is equal to 100 minus L by R of cell, where R of cell is called resistance of the cell. And these days we use digital conductivity meter, which gives conductance of the solution directly. Next we have using conductance and cell constant. K is calculated using the formula C. K is equal to conductance into G star, where G star is called cell constant, that is L by A. G star is equal to L by A, and conductance is called 1 by resistance. So by this we can write K is equal to G star is equal to L by A. So by this we can write K is equal to 1 by R, because Ck is nothing but 1 by R, into L by A. So this is the formula for finding K, that is conductivity. The molar conductance of the solution is calculated using the formula lambda m is equal to 1000 into K by C. So to find molar conductance of the solution, we have to use the formula molar conductance lambda m is equal to 1000 into K by C. And how we get K? K is equal to 1 by R into L by A. K is equal to 1 by R into L by A. I hope it is clear now. So this is called experimental determination of K using this. So you can note down the formula. I hope it is clear. Next, how to determine cell constant. Cell constant is determined by using a solution of known specific conductance. For this purpose, we'll use 0.1 normality KCl is used as reference, and the specific conductance of 0.1 normality KCl is equal to, that is potassium chloride, is equal to 0.0128 to Siemens centimeter inverse. So this value also no need to remember. Next, now we'll see the problems. 0.5 normality solution of a salt placed between two platinum electrodes 2 cm apart, having area of cross section 4 square centimeters, shows a resistance of 25 ohms. Calculate the equivalent conductivity of the solution. So here they are asking us to find lambda m, that is equivalent conductivity of the solution, and they have given concentration, that is 0.5 normality, and length is equal to 2 centimeters, A is equal to 4 square centimeters, and R is equal to 25 ohms. And now we are supposed to find, so this is L and this is A, and C is equal to 0.5 and this is R. So using these values, you are supposed to find lambda m. So for lambda m, we know the formula lambda m is equal to K into 1000 by C. K into 1000 by C. And K is equal to, how to calculate K, because K is not given, L by A into 1 by R. L by A into 1 by R. So first you have to find using the formula K. So L is equal to 2 centimeters. So K is equal to 2 by 4 into 1 by 25, which is coming around 1 by 50. 1 by 50. So use this value of K in the equation, second equation, lambda m is equal to 1 by 50 into 1000 divided by C, which is equal to 0.5 into 10 to no, 1000 only. 1000 divided by C, that's 0.5. 1000 divided by 0.5. So you will get the value of 40. So answer is equal to lambda m is equal to, that is equivalent conductivity of the solution is equal to 40. I hope it is clear. So they will not give K value, but they will give concentration value. And so this type of numericals are important for NEET. So 40 ohms inverse centimeter square inverse or Siemens centimeter square equivalent inverse. So it is clear now. Next question. So the electrical resistance of column of 0.05 molarity NaOH solution of diameter 1 centimeter and length 50 centimeters is 5.5 and 10 to the power of 3 ohms. Here they have given resistance R is equal to 5.55 and 10 to the power of 3, that is R value, and diameter is given 1 centimeter. From diameter you have to find area. A is equal to pi r square. So from diameter you can find R and d by 2 square. So you can use that formula for finding A, and resistance you know, length you know, length L is equal to 50 centimeters. So length is also given. So conductivity first, they are asking conductivity K and also asking molar conductivity lambda m. So for conductivity first, we'll take conductivity K is equal to 1 by R into L by A. So 1 by R, conductivity, conductance are the same. So K is equal to 1 by R value is 5.55 and 10 to the power of 3. And L by A is equal to, that is pi into pi value. So L is equal to 50 centimeters and A value is pi into, that is 3.14 into 1 by 2 whole square. 3.14 into 1 by 2 whole square. So after calculating this value, K is equal to, we got 0.011476 approximately. And then how to find molar conductivity? Lambda is equal to K into 1000 by C. K into 1000 by C. So since K is equal to 0. So substituting the value of K, 0.011476 into 1000 divided by C value is 0.05. So approximately you will get 230 Siemens centimeter square mole inverse. 230 Siemens centimeter square mole inverse. So I hope this is clear. So this is a model number 2. So answer 230 Siemens centimeter square mole inverse, because they have asked calculates conductivity and molar conductivity, and conductivity value 0.011476 is not given. Anyway, if it is correct, then only you get K value, that is lambda m. So I hope it is clear. Next question. So next topic we have, the conductance of the solution depends on two factors, that is number of ions in the solution, the speed of ions in solution under applied potential. So this is very, very important. The conductance of the solution depends on two factors, that is number of ions in the solution and speed of ions. So speed of ions in solution under applied potential. When you apply potential difference, how the ions will move, the speed, that is based on the speed of ions. So the conductance of the solution depends on mainly two factors, number of ions by and the speed of ions. I hope it is clear. Next we have variation of specific conductivity with concentration with increase in dilution. So as you dilute the solution, so with increase in dilution, the number of ions per unit volume decreases. Very, very important. They'll ask an objective point of view. So which of the following is true regarding specific conductivity? So the conductivity of an electrolyte, on dilution, with the increase of dilution, the number of ions per unit volume decreases. Therefore, the specific conductance decreases with the dilution of solution. So always the specific conductance decreases with the dilution of solution. So specific conductance determined by the letter lambda m or lambda equivalent. Variation of molar conductivity with concentration. So molar conductivity is nothing but given by K into the K by C. The decrease in concentration is more than decrease in specific conductance with dilution. So molar conductance increases with the increase in dilution of solution. So very, very important, these 2 points. Specific conductance decreases with the increase of dilution of solution, whereas molar conductance increases with the increase in dilution of solution. So these two are very, very important statements, specific conductance and molar conductance. Next, variation of molar conductance of strong electrolytes with dilution. Strong electrolytes. What are strong electrolytes? They are completely dissociate at all concentration. Means 100% dissociation. Alpha is equal to 1. That is, degree of dissociation is 100%, means it is equal to 1. So with increasing dilution, lambda, that is molar conductance of strong electrolyte, gradually increases and reaches a limiting value. So weak electrolytes. So weak electrolytes, already we know they are partially dissociated at a given concentration. So with dilution, the dissociation increases, producing more number of ions. So the value of molar conductivity for weak electrolytes increases rapidly with dilution, and for strong electrolytes it decreases. So here strong electrolytes they will get from limiting value. So this graph is very important. This graph is plotted between variation of molar conductivity with dilution, where root C is called concentration, that is normality or molarity. So lambda m was root C. For strong electrolytes, it is a decreasing with the limiting value, and weak electrolyte it decreases on dilution. Upon dilution, that is concentration. As the concentration increases, the limiting molar conductivity value decreases. As the concentration decreases, root C value, the molar conductivity value increases. So this is the variation of graph. This graph is very important for strong electrolytes. Means what are strong electrolytes? The electrolytes which dissociate 100%. That is strong acids, strong bases, salts obtained by the means of strong acid and strong base are all coming under strong electrolytes. And what are weak electrolytes? Weak acids, weak bases, and salt found by the means of strong acid, weak base, and weak acid, strong base. So this graphical representation is very important. I hope it is clear. Next, equivalent conductance at infinite dilution. What is equivalent conductance? In strong electrolytes, the value of molar conductance at infinite dilution can be determined by extrapolating the graph to zero concentration. But for weak electrolytes, the value of lambda increases sharply with dilution, and lambda infinity value cannot be determined by graphical method. This is overcome by Coriolis law. So, Coriolis law is giving it's very difficult to find the conductance of electrolytes. To find the conductance of electrolytes in a solution, Coriolis law is used. And what is this Coriolis law? This we are going to discuss now. So what is Coriolis law? At infinite dilution, when the dissociation of electrolyte is complete. See, for strong electrolytes, there is no problem because they dissociate completely into ions. So easily we can find out the conductance of all the ions in the solution. But weak electrolytes, we cannot determine the conductance easily, molar conductance, because the weak electrolyte dissociates partially. As we already know, weak electrolytes do not dissociate completely. It dissociates only partially. So due to this, what happens, it's very difficult to find the molar conductance of weak electrolyte. And to find the molar conductance of weak electrolyte, we'll use the Coriolis law. So according to Coriolis law at infinite dilution, when the dissociation of electrolyte is complete, each ion makes a definite contribution towards the molar conductivity of electrolyte, irrespective of nature of the other ion present in the solution. For example, lambda degree of AB. So lambda degree of M. Lambda degree of M means the infinite dilution, that is molar conductivity, limiting molar conductance is equal to lambda degree of cation plus lambda degree of anion. That is sum of its cation and sum of its anion. So in short, we can say what is Coriolis law. At infinite dilution, the molar conductivity or the limiting molar conductivity. So lambda degree means limiting molar conductance. So the limiting molar conductance of an electrolyte is equal to the limiting molar sum of the limiting molar conductance of its cation and and its anion. So again, I'm repeating the statement. At infinite dilution, in simple words, I'll tell you for our understanding. At infinite dilution, the limiting molar conductance of an electrolyte is equal to the limiting molar conductance of an electrolyte is equal to the sum of the sum of the limiting molar conductivities of its cation and limiting molar conductance of its anion. So I hope it is clear. So lambda degree plus lambda degree minus represent limiting molar conductance of any conductance of cation and anion respectively. So this is called Coriolis law. So in simple words, I'll tell you what is Coriolis law. Actually, to determine the molar conductance of strong electrolyte is easy because strong electrolyte dissociates 100%. Whereas in case of weak electrolytes, as they do not dissociate 100%, as they dissociate partially, we have to apply Coriolis law. How it is possible? I'll just show. So to find the weak electrolyte, since it's very difficult to measure the molar conductance or limiting molar conductance of weak electrolytes because as they ionize partially, so we will apply Coriolis law. What is Coriolis law? According to Coriolis law, the statement is at infinite dilution, the limiting molar conductivities of an electrolyte whether it is strong electrolyte or weak electrolyte, is equal to the sum of the limiting molar conductivity of its cation and sum of the and its anion, the limiting molar conductivity and of its anion. So I think it is clear now. So next we'll see here application of Cole's law. So for electrolyte other than univalent means that is monovalent. So lambda plus lambda V, that is number of ions, that is V is called V plus and V minus are respective stoichiometric coefficients of cations and anions. So for example, lambda degree of NaCl is equal to lambda limiting molar conductivity of NaCl. For example, let us take limiting molar example one I am discussing now. Limiting molar conductivity for NaCl can be calculated by using the formula based on Cornell's law is equal to limiting molar conductance of its cation, that is sodium ion, plus limiting molar conductivity of its anion, that is Cl minus. So lambda degree Na plus lambda degree Cl minus. What is lambda degree Na plus? Limiting molar conductance of sodium ion. What is lambda Cl minus? Limiting molar conductance of chlorine ion. So for example, if it is that is univalent, for NaCl it is univalent, whereas for aluminum sulfate you can see here limiting molar conductivity of aluminum sulfate is equal to 2 into, because aluminum sulfate dissociates to form, here I'm showing it how it comes to Al to SO4 dissociates to form 2Al plus 3 SO4 2 minus 2Al plus 3 SO4 2 minus. So this is the stoichiometric coefficients which we are taking B plus and B minus. So for aluminum sulfate, 2 into lambda degree, that is limiting molar conductivity of aluminum plus 3 into limiting molar conductivity of sulfate ions. So this is the formula for finding limiting molar conductivities for electrolyte using Coriolis law. I hope this is clear. Next, application. So what is the main application of Coriolis law? As we discussed, we can find out the limiting molar conductivities of a weak electrolyte to determine the molar conductance at infinite dilution of a weak electrolyte, because weak electrolyte does not dissociate completely. So to measure the molar conductance at infinite dilution for a weak electrolyte, it is difficult. So for that we are using Coriolis law. And second point, very important, determination of degree of dissociation of weak electrolyte, that is alpha. And for alpha, for how to find alpha for weak electrolytes, alpha is equal to K is equal to degree of dissociation. K is equal to C alpha square by 1 minus alpha, where K is called dissociation constant of the electrolyte and C is called concentration, alpha is called degree of dissociation. So you can find alpha using K values, and this K is not related to the K, that is conductance. This K is called degree of dissociation, that is dissociation constant of acid. Ka is called. That's why we write Ka there instead of writing Ka. So Ka is called dissociation constant of acid. If you write same K, it will be confusing. So I have written it as Ka, that is called dissociation constant of acid or dissociation constant of base or dissociation constant of electrolyte. So anyway, it is Ka is called dissociation constant. So by using this formula, we can find molar conductance and decay. So the application of Cole's law is nothing but we can find molar conductance of weak electrolyte, because it's very difficult to calculate molar conductance of weak electrolyte. So let us see one example here. Limiting molar conductance of the weak electrolyte is calculated by knowing limiting molar conductance of three strong electrolytes. So that only we are doing here. For example, you see, to calculate acetic acid is a weak electrolyte, we already know. So when you dissolve acetic acid, means acetic acid solution and dilution, it changes to CH3CO minus and H plus ions. And it's as it is not ionizing completely, it's very difficult to calculate the limiting molar conductance. So to calculate it, we have to take an indirect method. So already we know lambda degree m of CH3COH based on Cole's law is equal to, that is sum of its cation, limiting molar conductivities of its cation and limiting molar conductance of its anion, that is lambda degree of CH3CO minus, that is anion, plus lambda degree of H plus. And to calculate this, we can use the formula by using limiting molar conductivity of sodium acetate, sodium chloride, and HCl. So these are the three strong electrolytes. What are the three strong electrolytes? Limiting molar conductivities of lambda degree of CH3CONa, lambda degree of CH3CONa, lambda degree of CH3CONA. I'm writing here upward arrow. It is equal to this. Yes. Similarly, lambda degree of NaCl can be taken as lambda degree of Na plus and Cl minus, and similarly lambda degree of HCl. So for solving this problem, they will give the limiting molar conductance of all the strong electrolytes. That is three strong electrolytes. That is CH3CONA and NaCl and HCl. So by using these three, we can calculate, because here if you see here, lambda degree of Na plus minus lambda degree of Na plus gets cancelled. This and this gets cancelled. And similarly lambda degree of Cl minus and minus, this is minus of lambda degree, because minus of plus is minus. So lambda degree of Cl minus and plus lambda degree of Cl minus will get cancelled. So what is left over? Only lambda degree of CH3O minus and lambda degree of H plus. So which is nothing but lambda m of acetic acid. So I hope it is clear. So in this way, indirectly we will calculate the limiting molar conductance of weak electrolyte, because by experimental base also it is very difficult to find. So by applying Kohler's law, we can find limiting molar conductance of weak electrolyte. I hope it is clear. Now let us see some questions based on this. And to calculate degree of dissolution of weak electrolyte, we have to use the formula lambda m, where lambda m is called molar conductivity of the solution at a given concentration, and lambda degree m is the molar conductivity of the solution at infinite dilution. Lambda degree m is the molar conductivity of the solution at infinite dilution, and lambda m is called this. Abbreviation is very important, because what is given in the question you have to understand. So lambda m is called what? Lambda m is the molar conductivity of the solution at a given concentration, whereas lambda degree m is the molar conductivity of a solution at infinite dilution. By using these two values, we can find degree of dissolution of weak electrolyte, that is alpha. So alpha is equal to lambda m by lambda degree m. Note this formula, very, very important for objective point of view. Next. So to determine, as I already told you, the dissociation constant of the weak electrolyte, that is Ka, that is dissociation constant of the weak electrolyte, that is dissociation constant of acid or base. Ka is equal to C alpha square by 1 minus alpha, where C alpha square is equal to lambda m. So substituting alpha is equal to, here alpha is equal to lambda m by lambda degree m. So here I'm writing full lambda. Anyway, it is same lambda m, lambda degree m. So by substituting this alpha value in this formula, we'll get finally this Ka is equal to lambda m square, lambda degree m, lambda m square C by lambda degree m into lambda degree m minus lambda m. So it's better to find alpha value straight away, and then you can substitute Ka value easily. So in my point of view, first you calculate alpha, then substituting Ka is equal to C alpha square by 1 minus alpha for weak electrolytes. So I hope it is clear now. So this is very, very important. So from Kohler's law, the main two applications of Kohler's law is nothing but what? At infinite dilution, we can calculate the molar conductance of a weak electrolyte, first point. And second point, we also can also calculate the degree of dissociation as well as the dissociation constant of a weak electrolyte. So these are the two applications of Kohler's law. Very, very important. And to find the molar conductance of weak electrolyte, we will be comparing it with some other electrolytes based on the numerical. I hope it is clear now. Next. Let us see some questions based on Kohler's law. So calculate lambda degree of CaCl2 and MgSO4, that is limiting molar conductance of calcium chloride and MgSO4 from the following data. They have given limiting molar conductivity of calcium ion, that is 119, and magnesium ion, that is 106, and chlorine ion 76.3, and sulfate ions 160. So first we'll take lambda degree of CaCl2. Lambda degree of CaCl2 is equal to lambda degree of CaCl2 is equal to, by applying Kohler's law, we can say lambda degree of Ca plus 2 plus 2 into, because chlorines are 2 are there, so 2 into lambda degree of Cl minus. This is important here. So you can use the value, that is lambda degree of calcium ion is 119. So 119 is equal to 119 plus 2 into 76.3. 2 into 76.3. So which is coming around, you can do it. That is 271.6 Siemens centimeter square mole inverse. 271.6 Siemens centimeter square mole inverse. This is the unit of molar conductance, limiting molar conductance. Similarly, you can find limiting molar conductivity of MgSO4. Second point, second question that. So limiting molar conductivity of MgSO4 is equal to, so limiting molar conductivity of MgSO4 is equal to limiting molar conductivity of Mg plus 2 plus limiting molar conductivity of SO4 2 minus. Here there is nothing to multiply, so that's why directly we are taken, because both are equal charges. 106 plus 160, that is 266. So answer is 266 Siemens centimeter square mole inverse. Just note down in your note classwork. Now I'll wait for 30 seconds. Now you note down. In this way you can do. Now I'm clearing the data. So 30 seconds is over. Clear the data. So I'm clearing the data. In this way you have to sign. So we'll check the answers. I hope it is clear. So 271.6 Siemens centimeter square mole inverse and 266 Siemens centimeter square mole inverse. This is the basic problem from core last law. Basic problem. So sometimes they'll ask basic problem also for NEET. For JEE mains, they'll not ask this much basic problem. They'll ask twisted problem. Now this is very twisted problem. You can see here. They have given these type of questions are important for NEET as well as JEE mains. And JEE mains, in this they have given two problems. Actually, they will give one problem in the exam, and here they have given two problems. So these two problems will solve now. Now here what they have given, at 298 kelvins or 291 kelvins, whatever the temperature it might be, it is constant anyway. The molar conductivities, at infinite dilution of ammonium chloride, NaOH, and NaCl. So they have given three strong electrolytes, that is ammonium chloride, sodium hydroxide and sodium chloride are 129.8, 217.4, and 108.9 Siemens centimeter square mole inverse respectively. So the molar conductance of 0.1 molarity is also given, that is 0.1 molarity NH4OH is 9.35 Siemens centimeter square mole inverse. What is the percentage dissociation of ammonium hydroxide this dilution? Also calculate dissociation constant. This is very, very big problem. So they are asking us to find first alpha, then Ka also. But before finding alpha, we should know what is lambda m also. The lambda, that is molar conductivity and molar conductance of weak electrolyte, that is ammonium hydroxide. So how will you calculate molar conductance of the weak electrolyte? By using the values of the strong electrolytes. By applying Cole's law, we can calculate molar conductance of weak electrolyte. First, I'm trying to explain the problem. Just try to listen this carefully. First, we need to find in this question, we need to find, for finding alpha, we should know lambda m. And how to calculate lambda degree m? Lambda degree m by applying Cole's law. That is lambda degree m of NH4OH is equal to, by using the three strong electrolytes value, we can find lambda degree m of NH4OH. After finding lambda degree m, we can find alpha is equal to lambda m by lambda degree m. Then after getting alpha, we can apply the formula Ka is equal to dissociation constant. We can find, that is Ka is equal to C alpha square by 1 minus alpha. So all the three models have been given. So this problem is very, very important. But in the NEET or JEE mains, they'll cut either one first level or second level, and they'll ask third level also. So all the three levels, we are doing it now. So I'm taking a new slide for all the three levels. Just you can see here, and later on we can check. That is new whiteboard, that is new page. So you can see here, first what they are given in the numerical, lambda degree of NH4Cl. I'm writing everything here. You also copied on this. Lambda degree of NH4Cl is equal to 129.8. Take it as 1. equation 1. That is 1. Next, lambda degree of NaOH is also given 217.4 for that problem. So when I'm explaining this problem, so just you also note down in the classwork directly 271.4. It's not 14, 271.4. So when I'm explaining the problem, you also note down the steps as it is like that, so that easily you can understand after substituting. So please maintain this in your classwork. And lambda degree of NaCl is equal to, given what is given, I'm writing here, 108.9. And lambda m is given. Lambda m is equal to lambda m of ammonium hydroxide, lambda m of NH4OH, bracket, is equal to 9.35 Siemens centimeter square mole inverse. So by using these values, first we need to find lambda decayum of ammonium hydroxide, then we can find alpha for ammonium hydroxide, then we can find K, that is dissociation constant of ammonium hydroxide. So we need to find three problems. So three problems we have to find. So first what we have to find in this, I write here clearly, lambda decayum of NaOH, lambda decayum that is limiting molar conductance of ammonium hydroxide NH4OH. That is first. Second, we have to find alpha. And third, we have to find Ka. Ka is equal to how much? So these three we have to find using this data. So I hope it is clear. And they have given concentration also. Concentration is 0.04 they have given. So C is also given 0.04. Now 0.1 is given concentration. So first one we'll see lambda decayum of NH4OH. Lambda decayum of NH4OH. It is by applying Kohler's law. So we can do 1 plus 2 plus minus 3, because 1 plus 2 minus 3. That is, if you add lambda degree of ammonium chloride plus lambda degree of NaOH and lambda degree of minus lambda degree of NaCl, 1 plus 2 minus 3, we can get. So that is 1 plus 2 minus 3. So we can get lambda m of, that is limiting molar conductance of ammonium hydroxide. So already we know 1 is how much. How we got 1? Because I'll tell you this. So 1 is equal to lambda degree of NH4 plus, I'm substituting the formula here, lambda degree of NH4 plus lambda degree of Cl minus, that is first one, plus, and second one what we have, NaOH. So lambda degree of NaOH, that is lambda degree of Na plus lambda degree of OH minus, this is for second one, minus third one what we have, lambda degree of NaCl, lambda degree of Na plus lambda degree of Cl minus, Na plus. So by using this we can see easily lambda degree of Na plus, this one and this one gets cancelled. Lambda degree of Na plus and minus lambda degree of Na minus, this is also gets cancelled. Lambda degree of Cl minus, and this also gets cancelled. This is this one, because minus into plus minus. So what is left now here? Only we have lambda degree of NH4 plus and lambda degree of OH minus, which is required. So straight away we are substituting the values, 129.8 plus 217.4 minus 108.9 minus 108.1, third one, 108.9. So it is equal to 238.3. So already we know the values, individual values you don't have, we have the total electrolyte value. So same we are doing that. So if you are doing 1 plus 2 minus 3, you are getting limiting molar conductance for ammonium hydroxide, which is equal to 238.3 Siemens centimeter square mole inverse. Siemens centimeter square mole inverse. Now, what is the second question we have to find in this? Next we have to find alpha. So first one we got, second one now we are doing alpha. So next for that alpha also I'm adding one more slide. So alpha is equal to lambda m by lambda degree m. Lambda m by lambda degree m. So already we have found lambda m, And lambda m is given already, that is 9.35. In the first slide you can see lambda m is equal to 9.35. So substituting that lambda degree we have got already by using applying Kohler's law. So substituting that 9.35 divided by 238.3, which is equal to 0.039. So by this alpha is equal to 0.039 into 100, because we have to take degree of dissociation percentage into 100. So it is equal to 3.92. 3.92%. So this is the value of alpha. Now Ka is equal to, so second value 3.92 alpha value we got. So alpha is equal to 3.92. Next we have to find dissociation constant of the vehicle rate, that is ammonium hydroxide. So Ka is equal to C alpha square by 1 minus alpha. And C value they are given in the first question, you can see 0.1 normality. So 0.1 is into, and alpha is equal to 3.92%. So it is nothing but 0.0392, 0.039, because alpha value I will take 0.039 and percentage is 3.92. So alpha value is equal to 0.039, 0.039 into 0.039, because it is C alpha square divided by 1 minus 0.039. So which is coming around 1.599 into 10 to the power of minus 4. Convert it into tens powers, you can do it. So this is the value of Ka value. It is constant, it has no unit. So I hope this is clear. This type of 3 problems. Anyway, in the examination, they not ask 3 problems at a time. They'll ask either 1 problem, second problem, or third problem. So by giving any of this. So I hope all these models are very important for Kohler's law. Only these 3 only we have to do application for Kohler's law. Next I am doing next question. So for this answer is 3.92%, that is 0.039, and 1.59 into 10 to the power minus 4. So it is clear, and this type of question is very, very important. And for Neet or JEE means they'll ask us to stop either at limiting molar conductance of ammonium hydroxide by giving only the 3, or else they'll give the limiting molar conductance of ammonium hydroxide, and 0.1 molarity is also given, and this also is given. So it is clear now. Next, calculate the specific conductance of 0.02 molarity acetic acid, which is 2% dissociated. So they are asking us, they have given the molarity, and they are asking us lambda degree m is also given, that is limiting molar conductance at infinite dilution, and they are asking us to find specific conductance, that is lambda m. So simple it is. You can just see here what is the idea. So they have given alpha is equal to 2%, that is nothing but 0.02, that is 2 by 100. Alpha is equal to 2 by 100, which is equal to 0.02. Next, they are given what? Lambda m is equal to 390 centimeters, Siemens centimeter square mole inverse. Lambda dkm, that is limiting molar conductance. And from this, we can find out lambda m. So from the formula, alpha is equal to lambda m by lambda degree m. So lambda degree m is equal to given. By this, you can write lambda m is equal to lambda degree m into alpha. So that is equal to 390 into 0.02, which is coming around 7.8. Now, what they are asking us to find specific conductance is 7.8, and the solution specific conductance lambda m they are asking. So no, they are asking K they are asking. So lambda m is equal to K into 1000 by C. Lambda degree m is equal to K into 1000 by C. Lambda m is correct one. Lambda m is K into 1000 by C. So from this, we know the value of C also. From this, we can find K. So K is equal to lambda m into C by 1000. So substituting the formula, 7.8 into 0.002 divided by 1000, which is equal to 1.56 10 to the power of minus 5 Siemens centimeter inverse, 10 to the power of minus 5. So this is very, very important model. So simple, they'll give same model in the exam also. because only two steps conversion, but calculation part is more. Anyway, they'll give for this type of questions for JEE mains and NEET also. So what is the thing with you to calculate specific conductance? So if here the terminology is important. Specific conductance means what? It is K, and limiting molar conductance it is lambda m, lambda m. So first by using alpha we can find lambda m. After finding lambda m we can find K, because lambda m is equal to K into 1000 by C. So by using these two steps we can find out the answer. So I hope it is clear. You can copy down the solution and finally you can check the answer. It will be anyway, it is the same because I have calculated already. So in this way you have to proceed to the problem. This is model number 2. On these two models are very, very important for infinite molar conductance. I hope it is clear. Next. Yes. So K value we got it. Next we have, yes, continuation to this. So important recap. What is specific conductance? It is denoted by letter K. K is equal to L by A. L by R is equal to cell constant by resistance. Molar conductance mu is equal to 1000 into K by C. And resistance of the solution can be determined by meter bridge at circuit. That is R cell by R stand is equal to L by 100 minus L. Anyway, this third formula is not that much important. Till now, we have never got a question based on this third formula. And first and second already we know. Next, we'll see what is equivalent conductivity. Definition: it is the conductivity of all the ions present in a solution containing 1 gram equivalent mass of the electrolyte. It is denoted by letter lambda equivalent. So next we have the relation between molar conductivity and equivalent conductivity. So molar conductivity means with respect to molarity, and equivalent conductivity means with respect to normality. And for normality, we have to consider n factor, where n is the ratio of molecular mass to equivalent mass. So the molar and equivalent conductivity of sulfuric acid is related as limiting lambda m is equal to 2 into lambda equivalent, because sulfuric acid is H2SO4, so n factor is 2 because it releases 2 H plus ions. So n factor is 2. So sulfuric acid is equal to, so molar and molarity and normality, just like relation between molarity and normality. So molarity into molecular weight is equal to normality into equivalent weight. In the same way here, molar conductivity of sulfuric acid is equal to 2 into molar equivalent conductivity of sulfuric acid, because the n factor is 2 here. So this is clear. Next. Now we'll see some more examples based on this conductance, second question of electrochemistry. So here they are given, if the ionic conductance of Al plus and SO4 2 minus ions are X Siemens centimeter square equivalent inverse. Ionic conductance they have given, and Y Siemens centimeter square equivalent inverse. Calculate the molar conductance of aluminum sulfate, just like using Kohler's law. So Kohler's law, lambda m of aluminum sulfate is equal to lambda m of aluminum sulfate is equal to 2 into lambda degree of Al plus 3. Applying Kohler's law, 2 into, because it is aluminum sulfate 2 moles. So 2 into lambda degree of Al plus 3 plus 3 into lambda degree of SO4 2 minus lambda m only. So 3 into lambda m of SO4 2 minus lambda of lambda degree of SO4 2 minus, because based on Kohler's law. So this is 2 into 3, total it is 6. So lambda of Al plus is given X, and Y is given for the sulfate, it is given Y. So 6 into X plus Y. So 2 into 3, 2 into 3, because they're asking ionic conductance, 2 into 3 into bracket X plus Y. So which is equal to, here we should take X plus Y. So which is equal to, that is 2X plus 3Y anyway, the same thing you are getting. So which is equal to 6 into X plus Y. 6 into X plus Y. So this is the answer. The molar conductance of aluminum sulfate is 6 into X plus Y. Next. It's clear now. Now application of Kohler's law, determination of KSP. So still we are going higher level of numericals, because they can give easy to tough also for the mains and advanced as well as NEET. So how to find more about? That's why we have covered basic problems to high level problems. So easily you can use up these videos. The solution of sparingly soluble salt will be a very dilute solution, and hence the molar conductance of the solution is approximated to be lambda degree. And from Kohler's law, we know lambda degree of m is equal to lambda degree of plus minus lambda degree of minus, because the electrolyte. So lambda degree m is equal to 1000 into K by C, and C is the solubility. So from that we can find out C also, because lambda degree m is equal to 1000 into K by C. So C is equal to solubility of the salt. With from then, if C is equal to nothing but concentration, we can find out Ksp using the type of salt. So what is Ksp? That is solubility product. Suppose if Ksp of AB type salt is there, Ksp is equal to S square. For AB type salt, Ksp is equal to S square, that is C square. For AB type salt, AB type salt is very high, more complicated problem, but it's very easy also. This type of numerical also I have given him an example. So S square, that or C square, S square or C square, because both are same. Here C we are concentrating, so we can take the solubility is nothing but C. Next, clear the drawing. I'm clearing the drawing now. Next we have to do. So water undergoes dissociation also, we know, to some extent, because water is also an electrolyte. Dissociates to form H plus and OH minus. So for applying Kohler's law, molar conductivity of water is calculated. So if, this is the standard value. Molar conductivity of H plus, if it is 390, 350, and molar conductivity of OH minus is equal to 198. So we can use limiting molar conductivity of the water is equal to limiting molar conductance of water is equal to limiting molar conductivity of H plus and limiting molar conductivity of OH minus, adding. So we got 548 Siemens centimeter square mole inverse. K of water can be determined experimentally. So how it is determined, you can see here now. So limiting molar conductivity 1000 into K of H2 by H plus, and that is nothing but by knowing H plus concentration we can find Ksp of water. So that is dissociation constant also can be calculated by using H plus into OH minus by 55.5. How we got this 55.5? This is based on 1000 by molecular weight of water is 18. So 1000 by 18 we got 55.5. So this type of questions also important. So application of Kohler's law still more we are doing. Now we'll do some important models, high level models for advanced JEE mains and NEET. Very high level models you can see here. When a certain quantity conductivity cell was filled with 0.02 molarity KCl, potassium chloride, which has specific conductivity of 0.2768 ohm meter inverse, it had a resistance of 8 to 82.40 ohms at 25 degrees C. And with 0.0025 molarity K2SO4, it has a resistance of 326 ohms. Now calculate cell constant, conductivity of potassium sulfate solution, and equivalent conductance and molar conductance of potassium sulfate solution. So first, to find what is given here, I'm adding new slide. So new slide. So C is equal to given 0.002. C is equal to 0.00, sorry, 0.020. Only one zero after 0.0. So 0.020 molarity KCl, potassium chloride. That is C. Lambda degree M is equal to, given for potassium chloride, it is equal to 0.2768 ohm inverse meter inverse. Here very important, meter inverse they have given. We have to calculate this into centimeter inverse. Next, R is equal to resistance, R is equal to capital R, is equal to 82.4 ohms. So first they are asking us to find cell constant. So first question in this, cell constant. Cell constant already I told you, cell constant is equal to L by A. Cell constant is equal to how much? By using these three values you have to calculate cell constant. And this cell constant can be used for the same, because same cell is running for both the electrolytes. So that is potassium chloride as well as potassium sulfate. So first we have to calculate cell constant L by A. So L by A is equal to, we already know K is equal to, that is conductivity K is equal to L by A into 1 by R. So by this L by A is equal to, L by A is equal to K into R. Here this is ohm inverse, meter inverse is K. Actually, I have written wrong. Ohm inverse meter inverse, that is here. This 0.278 is given K, because molar conductance they are not given, they are given only conductivity K. So K is equal to 0.278. So by substituting this value, we can find out L by S, L constant is equal to 0.2768 into 82.4. That is coming around 22.80. Now, second, what we have to find K of K2SO4, because they are asking conductivity of K2SO4. And K2SO4 L by A into 1 by R. So that is 22.8, because cell constant is same, because same cell is using, that is very important, into 1 by R. And in this case, resistance is 326 ohms, which they have given already, 326. So by substituting, you will get the value 0.069. Now lambda is equal to, that is molar conductance, is equal to K into 1000 by C. So by using this formula, you can get lambda also. So all the three columns is over. So first they ask cell constant, second they ask conductivity, and third they are asking limiting molar conductance. So limiting molar conductance, alpha lambda is equal to K into 1000 by C, and C value of potassium sulfate, potassium chloride is given 0.020. So this is clear. Next. So 22.81, which you already got, and 140 ohm inverse centimeter square equivalent inverse, and 280 ohm inverse, because K2SO4 no 2 into 140. So if you find a lambda degree of potassium chloride 140, so K2SO4 means 2 into 140. That is K2SO4, because two potassium ions are there. So 2 into 140, it is 180, 280. Sorry. Next, how to calculate ionic product of water? That is, ionic product of water is equal to concentration of H plus into concentration of OH minus, and for molarity is equal to concentration of H plus is equal to OH minus. And how to calculate H plus concentration? Lambda m is equal to K into 1000 by C. Next. So calculation of equivalent conductance and molar conductance. This already we know. So this is just recap of the Colas law. So molar conductance is equal to X into lambda alpha of cation plus Y into lambda alpha of anion. And X of cation, lambda of cation, lambda of anion are the ionic conductance, and X and Y are stoichiometric coefficients. So for example, BaCl2 equivalent conductance is equal to molar conductance by 2, because equivalent conductance is equal to molar conductance by total charge. Total charge of barium chloride is Pa plus 2 or 2Cl minus. So either cations or anions we have to take. So this is a new formula. Whatever the models we are doing in the session, these models are more than enough for entire objective pointer. That's why I have taken the best models, which since many years you are getting. So if you can do this, understand these models and do this, you can answer any book, any objective book from this chapter is based on this concept. Even Faraday's laws also we have done the same way. So if ionic equivalent conductance given, number of ionic equivalent ion is equal to charge and then by total charge. So lambda is equal to number of equivalent cation. This is anyway the same thing, that is equivalent weight we have to, for normality and molarity we have to compare n factor. Now let us see the new question. Very, very important model. This is just mark important over here. So I'm marking, you also mark important over here. So very, very important. Lambda equivalent of 0.1 normality solution is given, and lambda equivalent of 0.1 normal solution is given, of calcium iodide is given 100 Siemens centimeter square equivalent inverse at 298 kelvins. G star is nothing but what? Cell constant. G star is called what? Cell constant. G star is L by A. L by A is equal to 0.25 centimeter inverse. And how much current will flow when the potential difference between the electrode is 5 volts? Till now, we have not done current question based on this. From this also you can find current. That's why it's very, very important model. And this model is most important, so we can do it here. So they have given what? Lambda equivalent of calcium iodide, that is equal to 100 Siemens centimeter square equivalent inverse, and L by A is equal to 0.25 centimeter inverse, that is cell constant. From this you can find out first K, because if you find out K is equal to L by A into 1 by R. So if you calculate K, from K we can calculate resistance, because For current, we require I is equal to V by R. So for current, we require I is equal to V by R by applying Ohm's law. That's why this topic is different. Simple topic only. So from Ohm's law, we know I is equal to V by R, that is current is equal to V by R. Then they have given voltage also 5 volts and our resistance we have to find. Because from this, using this given data, we have to find resistance. So K is equal to L by A, that is 0.25 into 1 by, just I'll do it again. So K is equal to L by A into 1 by R. So by this we can write K is equal to lambda into C by 1000. First we have to find K value. So first step we have to find K value. K is equal to lambda into C by, lambda is equal to K into 1000 by C. Lambda is equal to K into 1000 by C. Because lambda equivalent is given, and from this we can find K first. So lambda equivalent is given, that is how much? So K is equal to lambda into C by 1000. K is equal to lambda into C by 1000. So they are given lambda is equal to 100 into C, that is given already 0.1 by 1000. So by substituting we got 0.01. So this is the value of K, Siemens centimeter square. So no need to write the unit again. So this is the value of K. Substituting the value of K in this equation, because we'll get resistance. After getting resistance, we can find out current easily because they have given voltage. So for solving this problem to find current, first we need to find K value. After finding K value, we can find the resistance value by using the formula K is equal to L by A 0.025, that is L by A is also known, and 1 by R. So from this we can find out R, and R value we got it as 25 ohms. After substituting this, we got R is equal to 25 ohms. That is 0.25 into 1 by R is equal to 0.01. So R is equal to 25 ohms. Now we can easily find out I value. I is equal to V by R. So since I is equal to V by R, their place is not there. That's why I'm mapping. Next, we have to find I is equal to V by R. So since R is equal to, we got it. I is equal to V by R. Substituting I is equal to V is given 5 volts by 25. So it is equal to 1 by 5, 0.2 amperes. So this is the answer. So this is very, very typical problem. They have given two chapters link, that is electrochemistry only, but they have suddenly jumped into Ohm's law. So that's why this type of linked questions. Ohm's law is very basic, even in 10th class it is there. That's why even though we don't have, so NEET students also can do this type of question. They have given lambda equivalent of 0.1 normal solution of calcium hydride is given 100 Siemens centimeter square equivalent inverse. From this we have to find K, and the G star, by using G star and K we can find R, because finally we have to find current. So 3 steps involved in this. First step, we'll find K value by using the formula lambda is equal to K into 1000 by C, because K is equal to lambda into C by 1000, and lambda into C, because lambda is given 100 and C is given 0.01, 0.1, and by 1000 you can find out lambda. So K value. After finding K value, since conductivity K is equal to, from law of resistance, L by A, that is L constant to 1 by R, and straight away they given G star. G star is nothing but L by A, so 0.25. So 0.25 into 1 by R is equal to K. K value already we got it from this first equation. So by substituting that value, we'll get value of K, R value, and R value we got it as 25 ohms. After that, straight away simply current flowing, that is I is equal to V by R. So 1 by, so this 5 by 25, which is equal to 1 by 5, which is equal to 0.2 amperes. So I hope it is clear now. So just note it down. 3 steps involved. First step we'll find lambda. Second step we'll find K. Second step we'll find, from first step we will find K value, conductivity. Second step we are finding resistance from K, and third step we are using that resistance value in I is equal to V by R formula and finding out current. So these 3 steps. I hope this problem is clear. Very, very important model. So even you may expect these models in the examination also. So let us see the answer now. 100% is 0.2. Yes, 0.2 amperes. I hope it is clear now. Next, This is very simple one. The resistance of solution A is 50 ohms and that of solution B is 100 ohms. Both solutions being taken in the same conductivity cell if equal volumes of A and B are mixed. So volume is 2 times because equal volumes is there means 2. So calculate the resistance of the mixture using same conductivity cell. So assume that there is no increase in degree of dissociation. This is looking wise it is very difficult, but if you apply by using this resistance, that is nothing but total resistance is equal to 1 by R. So resistance is equal to 1 by R is equal to this resistance in parallel, that is 1 by R1 plus R2. Resultant resistance is equal to 1 by R is equal to 1 by R1 plus 1 by R2 for parallel series. And this is not a series circuit. 1 by R is equal to 1 by R is equal to 1 by R1 plus 1 by R2. So by substituting this formula, we got resistance as, so 1 by R1 plus 1 by R2. Straight away we can substitute. You'll get 100 by 3. So which is equal to resistance is equal to 66.6. So 3 by 100 and total resistance is equal to 2 into this 3 by 100. 100 by 3. So R is equal to 100 by 3. Since 1 by R is equal to 3 by 100. So resultant resistance R is equal to 100 by 3 into 2 because equal volumes they are given. So that's why we have to multiply with 2. So straight away we'll get 100 by 3 is 33.3 into 2 is 66.6. So answer is 66.6 ohms. So I hope it is clear. Next question. So very important question. As I told you, we can easily calculate solubility product also. They have given the specific conductance of solution of silver chloride is 2.28 in 10 to the power minus 6 Siemens centimeter inverse. Calculate the solubility product of that is KSP of AgCl, and they have given lambda degree of AgCl is given. So KSP we have to find. So lambda degree of AgCl. So this numerical. So first we have to find C value because they have not given C. Because if you find C value, automatically we can find KSP because KSP is equal to C square. Because KSP is equal to C square. So K into lambda by C is equal to K into 1000 by lambda because K lambda is equal to C K into 1000 by C. So C is equal to 2.28 in 10 to the power minus 6, that is C, K value is given into 1000. And lambda value is also given, that is 138.2. So by calculating this, we got it as 0.016 in 10 to the power minus 3. And so KSP is equal, sorry, is 1.6 in 10 to the power minus 5. 1.6 in 10 to the power minus 5. Yes. So now KSP is equal to C square because this is the salt of type AB type. So C square. So C square is equal to 1.6 in 10 to the power minus 5. Approximately I'm doing it into whole square, which is coming around 2.68 in 10 to the power of minus 10. So this is the answer for KSP. So this type of questions is important. They have given specific conductance. Specific conductance denoted by letter K. So they have given K value. K is equal to 2.28 in 10 to the power of minus 6. And they have given lambda also. So from using K and lambda, easily we can find out C because C is equal to, so K is equal to, sorry, lambda is equal to K into 1000 by C. From that, we can find C is equal to K into 1000 by lambda. So we can find out the value of C, which is coming around 1.6 10 to the power of minus 5. Here I have used, I have calculated already, but it will take time in the examination. So 1.6 in 10 to the power of minus 5. So KSP is equal to, because the salt of type AgCl is silver chloride is AgCl is AB type. If it is AB2 type, we have to use 4SQ, that is 4CQ. But this is AB type, so you have to use only C square. So C square is equal to 1.6 10 to the power minus 5 whole square, that is 2.68 in 10 to the power minus 10 approximately. So I hope it is clear. So all these models using core loss law and conductivity and conductance, all the models we have done, possible models we have done in this lecture. So use these numericals and use this type of numericals and understand and apply this concept in the Jayendra material or Jayendra rank zone. I hope this is clear. I am ending this class. Ending this class. So lecture 2 is very, very important. Lecture 1 is also important. Thank you all.